Hello, my name is Christian Adam. I'm the head of the Division 4.4, Thermochemical Residues Treatment and Resource Recovery. And I would like to introduce you into this division and show you our technical center, the equipment we have, and also some trials we carry out here in the division. Okay, then please follow me. Okay, and here you can see our technical center. Of course, we operate some ovens like muffle furnaces and rotary kilns, tube furnaces, and also fluidized bed furnace, and a technical scale electric arc furnace, which is a kind of unique aggregate because of its size. We can go up to temperatures of 2,500 degrees Celsius and operate with a capacity of 150 kilogram per hour. Yeah, we are working on different projects and topics such as scandium recovery from red mud. We look at scandium, how is it bound to the different minerals in red mud. We have a project on tantalum recovery from tin slags and other residues, where we operate this electric arc furnace, and we will show you later on a trial about that. We have a project that investigates how we can produce cementous materials from steelworks slags, and also how to recover the filter dusts and sludges from steelworks and produce zinc materials from that and return iron and carbon into the process. So we are going towards zero waste in steel industries, we would like to say. We have also projects how to recover phosphorus from sewage sludge ashes. We make fertilizers out of it that have less pollutants, and we care for good plant availability of the phosphorus compounds inside. Okay, I would suggest to go down into the technical center, and then you can see everything, and we can show you the trial we performed today. Okay, then follow me, please. This is the entrance to our technical center, and of course, to enter this technical center we have to think about protective clothing. You can see this flashlight here. This shows us laser activity in the technical center, and before we enter this technical center we have to wear protection glasses against laser light. Hello again. As I told you before starting such an experiment with an electric arc furnace, we have to wear protective clothes. These clothes are fire resistant and heat resistant. Of course, also gloves and a helmet, as you can see here. In the following, we will use this electric arc furnace to melt down residues like tin slags that contain tantalum, and we introduce carbon as a reductive and reduce tantalum oxide and niobium oxide to the carbide form and transfer it into a metal phase that is then separated, and tantalum and niobium are concentrated in this metal phase and are then further processed. And in this trial today, we will use laser-induced breakdown spectroscopy to follow this procedure. So we want to measure tantalum and niobium in the hot melt. Okay, so we finished the trials with the tantalum recovery, but of course we have other topics. For example, we work in rotary kilns, and one of the topics is phosphorus recovery from sewage sludge ashes, and this topic will be explained by my colleague Stefan Kugler. Okay, see you.
Hello, my name is Stefan Kugler. I'm a process engineer and I work for BAM in the project Loop, which main focus is to recover phosphorus from sewage sludge ashes. And today I'm going to show you how we do that in our rotary kiln. Sewage sludge ashes contain about 6 to 12% phosphorus, depending on the country where it's coming from or how the wastewater treatment plant is run. And the phosphorus in sewage sludge ashes is mainly tricalcium phosphate, which is not very good plant available. So we have to transform this kind of phosphorus form into a highly plant available form, which is calcium sodium phosphate. To transform tricalcium phosphate into calcium sodium phosphate, we need a thermochemical reaction, which we induce in our rotary kiln here. We also need two more ingredients. The first one is sodium carbonate, for example, which is our sodium donator for the main chemical reaction. And the third one is dried sewage sludge. This ingredient contains a lot of carbon, which reacts with the oxygen in the atmosphere to carbon monoxide. And this is a strong reducing agent. And we use that to reduce the heavy metal oxides into their elementary form, which then evaporate with the off gas at high temperatures. The way this rotary kiln is working is by the rotation of a tube and an inclination. So we put our three ingredients in the back, in the feeder, and by the rotation and the inclination, the material gets transported through the tube, and we try to adjust the process parameters in a way that we get a retention time of 30 minutes at 1000 degrees Celsius. After the thermochemical treatment in the rotary kiln, we receive a product rich in highly plant available phosphorus. Here in the lab, we do experiments to determine the actual performance of our potential fertilizer in different kinds of soils and in direct comparison to other common fertilizers, like the highly water-soluble triple superphosphate. The first results of these experiments, they prove that our phosphorus fertilizer is water insoluble and stays in the soil, which is a basic requirement for further processing to so-called next generation fertilizer. Next generation fertilizer, unlike conventional fertilizers, don't get washed out and supply plants according to their needs, and so prevent problems like eutrophy and overabundance of nutrients in groundwater. If you want to know more about the project Loop, just visit our website. Here you can find more information about the project itself, the work of BAM and the cooperating project partners. Thank you very much.
Was haben wir noch? Was habe ich vergessen? Das kann man schneiden, oder?
For BAM in the project Loop.
Dann auch noch mal vorne machen.